Hello, thank you for attending this presentation. My name is Dimitrios Kosmas, and on behalf of the Robotics and Mechatronics Group of the University of Twente, I will be sharing our work on the development of a 3D printed capacitive force sensor aimed to assist in a partial knee replacement surgery. First, we will have a brief introduction to the project. The topic of balancing unicompartmental knee arthroplasty focuses on relieving symptoms of knee-related arthritis as an alternative to the more traditional total knee replacement. When applicable, the partial knee replacement incorporates smaller implants, which reduces the amount of bone required to be removed, subsequently minimizing the overall damage that is induced. During the surgery, the orthopedist makes use of a spoon-shaped device, referred to as the gap gauge. These gauges come in various thicknesses, as a means to address the different knee sizes. The goal during this step of the surgery is to assess the distance between the tibia and the femur bones, such that the gap is equivalent to positions, flexion and extension of the unloaded knee. Equivalent distance guarantees the proper function of the polypropylene bearing implant that is located between the metallic parts of the final prosthesis. In this work, we make use of additive manufacturing as the fabrication technology. Additive manufacturing, or 3D printing, is known for a number of key advantages, like design freedom, which enables the fabrication of complex shapes, as the one shown in this figure, representing a sculptor's recreation of a spike fossil, rapid development cycles, and, amongst others, the possibility to realize geometries with personalized features. In particular, out of several 3D printing fabrication technologies, we make use of fused filament fabrication, which is one of the most common and accessible methods, where molten thermoplastic is pushed through a small diameter nozzle to form objects layer by layer. When these thermoplastics are infused with carbon, they can exhibit conductive behavior, and combined with multi-material techniques, sensing can be integrated into almost any geometrical structure, like the one that we see in this figure, showing a 3D printed EMG armband, which was developed within our group. The motivation behind this project is the hypothesis that for the longevity of the prosthesis, the applied force by the ligaments in both flexion and extension of the knee should be similar and within a certain range. Currently, this force is experimentally estimated by the surgeon based either on the felt friction during the gap gauge insertion or based on the reaction force when attempting to raise the gap gauge while in place. Therefore, the objective of this work is to develop and characterize a gap gauge with embedded sensing in order to quantify the normal force applied by the ligaments, and we will do that by using multi-material fused filament fabrication technology. With the context introduced, we first have to define the application requirements. As discussed, the gap gauges come in various thicknesses. With a proof of concept prototype in mind, we focus on thickness of 3 mm and above, as means to ease the fabrication process. Second, the target force range to be sensed is set from 2 to 12 newtons, and this is experimentally validated with the help of the surgeon and an artificial knee setup fitted with an off-the-shelf load cell. Third, given the non-linearities exhibited by filament-based 3D printed sensors, we aim for a sensing principle and configuration that could eliminate most of the undesired effects, such as hysteresis, creep, and drift. And fourth and last, by integrating sensing into the spoon, we consequently allow a certain degree of deformation, such that a signal can be produced. In order to maintain trust on the gap gauge's thickness rating, and after dealing with the orthopedist, a maximum of 10% deformation is set as the allowed limit. Next, the sensor design and fabrication will be discussed. For the sensing principle, a capacitive approach is chosen in this case. Often, a piezoresistive approach is also suitable, but from the literature it is shown that filament-based piezoresistive sensors exhibit highly nonlinear response, which would violate the set specifications. Capacitive sensing have shown to be less influenced by the viscoelastic properties of the polymers used, and therefore exhibits less nonlinear behavior in the response. On the other hand, capacitance readout interfaces are more complex compared to their piezoresistive counterparts. With all that in mind, a parallel plate capacitive sensor is chosen in a differential configuration with 3 plates. Here, the middle electrode acts as a common ground plane. The exerted force is designed to be normal to the sensor surface, reducing the distance between the electrodes upon application. In the cut of the sensor, in the bottom left figure, the embedded structure is exposed, where we can see the sensor body the dielectrics, the contact pads and traces, and of course the electrodes. In the figure in the middle, the network interface of the sensor is shown, with RT denoting the contact traces resistances. Last, by taking three assumptions, it's straightforward to derive an analytical description of the expected capacitance change. That is, assuming stiff electrodes, compressible dielectric, and very small displacements, where we allow ourselves to work on the linear range, where the capacitance change could be expressed by the following equation. From here, the fraction delta C over F can be seen as the sensor sensitivity expressed in femtofarads per newton, in this case, per newton. Moving on, we can discuss the sensor fabrication. A 4-material task is carried out in a Abayazid series 3D printer. As illustrated, the printer operates in the basis of a rotating turret, where tools are located along its circumference. The body of the sensor is made from a generic PETG filament. The conductive components are treated with protopasta conductive PLA, and the dielectrics are made from different TPU polymers, NinjaFlex and X60 in this case, as means to impose non-equal responses from the two capacitances. For the prototype, the main dimensions are shown in the top right, from which the expected sensitivity can be calculated to be 9.1 femtofarads per newton. In the bottom right figure, we can see the fabricated sensor, first as it was fabricated, and in the second figure with minimal post-processing, where the readout cables are attached by melting some stranded wire into the contact pads. Okay, next we'll have a short overview of the experimental setup. The main components of the experiment are a PC equipped with MATLAB software, where readout and post-processing scripts are made, the 3D printed sensor, loaded in the normal direction with a SMAC linear actuator. On the tip of the actuator's stroke, a load cell is attached in order to more accurately measure the force. A plastic tip is then used as the contact medium with the sensor. To read out the sensor, an off-the-shelf capacitance to digital converter is employed, which in turn is interfaced with an 8-bit microcontroller, an Arduino Micro in this case, which streams data over to MATLAB. Then the raw actuator encoder channels are extracted and read by a digital oscilloscope as means to evaluate the stroke position. Last, the force signal is read by all measuring devices. The response of the load cell is fed both into the scope and the Arduino, and the force as returned from the SMAC controller is also read by MATLAB. During post-processing, the sampled force from all the devices is used to synchronize all signals in respect to each other. With the setup described, we can now move on to the results. For this work, the sensor is characterized under dynamic loading condition. A sine wave is used at a 0.2 Hz frequency with an amplitude of 10 newtons. The first figure describes the filter capacitance response versus time in contrast to the exerted force input. At first sight, we see a satisfactory follow of the input, although the external response is varying in an unpredictable manner within a certain interval. From this data, the measure sensitivity is found to be 9.5 femtofarad per newton, which falls quite close to the estimated one of 9.1 femtofarad per newton. The figure at the right shows the input-output relationship of the cyclic loading, clearly exposing the hysteresis of the system. Here, a max error of 16.5 femtofarads from a linear feed shows a significant drop in accuracy when continuous measurements are concerned. Now we can conclude with a short discussion. First, we saw a good correspondence between the design and measure sensitivity. Second, for low frequencies below 0.2 Hz, and by focusing on the loading part, the sensor exhibits relatively low non-linearity when compared with other filament-based approaches from the literature. Hysteresis is still present, significantly reduces the sensor performance. So if repetitive measurements are of interest, then methods of hysteresis compensation are advised. Fourth, overall, given the application specifications, the prototype sensor seems to be potentially suitable for the task. Towards future work, we will focus on application-specific characterization by means of testing under static loading conditions, investigating the effects of embedded active shielding, as well as examining possible sterilization methods, compatible with filament fabricated devices, of course. Finally, the acknowledgements. Following are the references to the external content and images used within this presentation. And this work has been in a close cooperation between the University of Twente and the Deventer Hospital in the Netherlands, and it was made possible with the support of the Pioneers in Healthcare Fund. Thank you all for your attention.